Okay, I would like to thank everyone for attending the Electronics Packaging Conference. My name is Zachariah Peterson. I'm with Northwest Engineering Solutions, and I'm going to be talking about causal transmission line geometry optimization for impedance control in printed circuit boards. So, in looking at design optimization, and especially in the research literature, one thing that you often see with the application of optimization techniques for transmission line design is they're normally used for regression, where you start with some experimental data and you want to extract some model parameters. For example, in the standard 802.3 model for channels on printed circuit boards. So I would like to go the other direction, to start with some model and then to use optimization for broadband design. And this is actually quite important for obeying manufacturability constraints, signaling standard constraints, etc. So here the goal is to balance some broadband signal integrity metrics with impedance matching. And I'm going to focus on impedance matching here in this presentation, but you could pick some other design goal if you like. And this is important because newer signaling standards are actually placing constraints on broadband quantities, and they demand broadband design techniques. And so I'll show an example here in a moment. So when we look at something like 112 gigabit per second PAM4 signaling, here you can obviously see the power spectral density is spread out over a very broad range of frequencies. The Nyquist frequency is much smaller than 1 over the rise time. So where you cut off the bandwidth is a bit arbitrary here. I think you could certainly say that it's limited by the receiver. You could essentially put it wherever you like. Here, the goal is to then design channels and even integrated circuits themselves to accommodate some portion of this bandwidth. And here we need to then choose some cutoff and determine what happens on the transmission line at all frequencies up from DC all the way to the band edge. So your design goal could be insertion loss, it could be return loss for a shorter line, it could be anything you like, as long as it's relevant to your signaling standard. And so as an example here for a newer signaling standard in USB 4.0, we actually have a dual objective design optimization problem. This dual objective problem uses 2-port S parameters and multi-port S parameters in designing differential pair channels. So the goal in a USB 4.0 channel design is to minimize integrated return loss, which is defined as a broadband quantity. You can see here in this integral, it spans from DC all the way up to a very high frequency limit and accounts for insertion loss and input and output return loss. Similarly, for integrated crosstalk uses cross-port insertion loss, so you have these SIJ terms, and it's also a broadband quantity. And to do this properly, you need to have some model that describes either the integrated return loss or the S parameters, or the integrated crosstalk, or the impedance. And I'm going to focus on impedance momentarily because impedance is actually quite important to all of these other quantities, as we'll see here shortly. So if you can start with a numerical model, or you can start with an analytical model that's linked back to the geometry and the structure of your printed circuit board, you can then do real design optimization, ideally without having to do design exploration with a field solver, or by having to do some regression technique back from a large number of experimental measurements. So when we look at Interconnect Optimization, there are many parameters on any PCB transmission line. So here I've just shown on the left a microstrip, on the right we have a strip line, and the graphs on the bottom of this slide correspond to the microstrip line. I'm actually going to address the strip line here momentarily in this presentation. So some of our design goals here could be impedance mismatch, they could be dispersion, they could be crosstalk. In the graph on the lower left, this is a design that's been chosen for impedance mismatch optimization. So we want to minimize the impedance mismatch with respect to a target. And this was done with the method I'm going to outline here in this presentation. This microstrip line was designed to 50 ohms target impedance. And so you can see in the real part of the impedance, it's actually a pretty good design over a very broad range of frequencies, while still accounting for sources of loss and dispersion in the dielectric. And so you can see I'm within 1% plus or minus. Here we have reasonably consistent imaginary part. On the right graph, we have the phase of the transfer function, and you can actually see on a much shorter line, there are some portions of the relevant bandwidth that have relatively flat phase, so we can expect low distortion in those bandwidths. So, for example, from about 12 to about 18 gigahertz. So to get started with something like impedance mismatch, which I'll be focusing on here, we need to look at the RLCG model, which is the standard model from transmission line theory, and get the impedance for our transmission line, and then also we'll get the propagation constant. And so within the RLCG model, we have 4 different parameters, which really are broadband parameters. Normally, if you look at the transmission line theory, the resistance just accounts for DC resistance, but real channels, including the specifications within 802.3 standards, specify accounting for skin resistance. They don't state this explicitly, but that's basically what you're accounting for, is the skin resistance of your channel. Then we have dielectric losses, that's the G term. Here with L, our inductance term, we have an inductance at infinite frequency. Here we're assuming a non-magnetic substrate, so L infinity will just be some constant. And then here with our capacitance, our C of omega, we have this term here, this K sub G factor. So this is a geometric factor that just accounts for the fringing field from the conductor back to its reference plane. And then we have our dielectric constant. Now, the important point in any model that we want to use for broadband design, and whether it's impedance mismatch minimization, or whether it's minimizing, let's say, phase velocity dispersion or group velocity dispersion, or whatever signal integrity metric you want to optimize, we need to have causal models for all of these different quantities. And so the first being here, the dielectric constant, we'd like to have causal dielectric constant. Second, we have a source of loss here that's not normally accounted for in the literature, but that is copper roughness. This is something that's become quite important in CAD tools and within the PCB community to model properly. And then those two will fit into our electrical parameters, as I will show here momentarily. So I'd like to focus on copper roughness just briefly. Copper roughness does fit into the above model, and it will fit in here with the skin resistance. Basically, the effect of copper roughness is to increase your resistive losses. And here, I've shown a AFM image on the right. This was taken from one of Yuri Shlepnev's older DesignCon presentations. But here on the left, we have an AFM image. Here, the important quantity to look at is the root mean squared variation across the surface of electrodeposited copper across the surface. And we're going to use this root mean squared variation in height to determine the losses produced by copper roughness. Then we also have the actual particles that make up copper, which also need to be included. And so this is shown in the SEM image on the right. It's basically just a zoomed in version of whatever you'd be measuring on the left. And here, you can see it's maybe 1 to 2 micron particle size in this SEM image. So we have some average here that we can look at. So we can use these values within an analytical model that builds our copper roughness correction factor. And so in this example, I'm going to use the Cannonball-Huret model. However, one of, I believe, Yuri Shlepnev's recent DesignCon presentations from this year, in that presentation, he looked at tabulated data for the copper roughness correction factor. And so this arises because here the real thickness of our dielectric depends on the average roughness, not on the nominal thickness that we would like to have. And so because of that, we need to include this in our dielectric constant. This is a simple model that does this, which you can derive with some simple algebra. However, you could also use a tabulated value for your dielectric constant directly from a rough interconnect on a PCB substrate. However you get that data, it doesn't really matter. In my method, I just used these a bit simpler methods to account for copper roughness. And so, since I care about impedance mismatch in my method, and no matter which signal integrity metric you want to address in your design, you'll need the impedance anyways. So I've gone through and looked at how to take what would be a dispersionless impedance formula in terms of the geometry and convert it into a model that then accounts for dispersion and roughness in the real impedance. So to do this, I've just started with two identities from transmission line theory, which are the velocity and then the dispersionless Z0, the dispersionless characteristic impedance. And so to then get to a model that accounts for roughness and dispersion, here we have two equations and two unknowns. All right, so our first unknown is L infinity. Our second unknown is K sub G. What we can do then is just solve for K sub G and L infinity, and then we'll use a linear transformation to add back in the skin effect and copper roughness, and then we will rederive a new impedance in terms of the old impedance. And so I'm going to show this here in the next slide. So here we want to include losses with a linear transformation. Our inductance is simply the characteristic impedance divided by the speed of light in the material, in the PCB substrate, I should say. Now we can take a linear transformation once we know L of infinity, and we have the numerator in the characteristic impedance equation from transmission line theory. Do the same for the capacitance. We now have the denominator from the impedance equation from transmission line theory. And so just divide those two things, and now you get a equation that accounts for copper roughness and dispersion in terms of the nominal impedance without roughness and dispersion. And so this Z0 characteristic impedance without roughness and dispersion, if it's already defined in terms of geometry, now you have everything you need for design optimization over a very broad bandwidth. And we can do the same here with the propagation constant. So again, instead of dividing these two terms, we just multiply them, take the square root, and now we have our propagation constant. So here we want to look at impedance deviation minimization. Obviously, impedance being a function of frequency, we need to consider the entire bandwidth. And so to do that, we can use the LP norm. An LP norm is just a way of looking at the integral of a function with respect to some target. Here for p equals 2, it's just equivalent to minimizing root mean squared deviation from a mean value. So here in my stripline problem, what I've done is I've started with an 8-layer stack up, and I have chosen a 25 centimeter line. I've constrained my my copper thickness based on the copper weight. So this is all standard in PCB manufacturing. And I want to look at impedance deviation from a target impedance. And so I've chosen 50 ohm termination. Again, this is standard. I'm accounting for a 1 picofarad load capacitance, so a bit high for modern integrated circuits, but this will actually become more important when we look at the transfer function and causality. Here for my geometric constraints, I've just set from 0 to 6 for the width divided by the height. This is actually quite important from Waddell's transmission line equations, which are known to be very accurate over a broad range of frequencies. But here, just accounting for this ratio is actually very important in those models. Accounting for that ratio reduces your computation time because you basically have one variable you're working with instead of two. Here, T and H, I've left them fixed based on my chosen stack up. You could also use the T and H as an optimization variable, so you could look at that ratio. T over H is also an important ratio in Waddell's transmission line models. And you would then need to vary those among some integer values. So it makes the problem a bit more complex. And I'm using a two-pole Lorentzian model to account for the dielectric constant of a purportedly smooth substrate. However, I then showed how to include a simple model for copper roughness as part of this design process. So here, my design optimization problem obviously requires an optimization algorithm. Here, I'm using a standard differential evolution algorithm that you can find. You can develop your own from Storn and Price. I'm just using their mutation procedure. Here, I've included constraint checking, which is actually quite important, especially in a problem like this. We want to make sure that we stay in the solution space. And you could certainly use something else like another genetic algorithm or particle swarm optimization or something like this. So here with my optimization algorithm, I can now do my design optimization. And so I get some interesting results. And we actually see here for a rough line with dispersion, I get pretty good impedance matching with low loss. And it's actually similar width as a smooth line. So the smooth line just has no roughness and no dispersion. And I've just taken the dielectric constant at 1 gigahertz. And so even with roughness and dispersion, we get some good matching with low loss. However, here in the insertion loss and return loss graphs, I can see some resonances in the return loss, and they actually get very severe in the rough line compared to the smooth line. And so you can see a bit better how those resonances arise due to the slightly larger mismatch in the rough line. So here, and this is my last slide looking at model results. I'm looking at causality. Just from looking at the input pulse, which is a standard IEC input pulse, you can see how that then evolves into an impulse response in the time domain. If in this zoomed in panel, you can see that indeed there are some causal artifacts left over, or I should say non-causal artifacts left over in the smooth line, whereas the rough line, using this procedure with causality enforced, you actually do see very nice results here in the impulse response. So some drawbacks in the current model, we don't account for anisotropy and inhomogeneity in the dielectric constant, which arises due to the fiber weave effects. And obviously in a real situation, there's going to be many more objectives. So I've listed 4 here, and I'm sure you could come up with some other objectives if you really think about it. Looking ahead, you could use something like neural networks for prediction. This could account for more complex models involving multiple signal integrity objectives, as well as more complex geometry, materials, manufacturing processes, etc. So thank you everyone for listening. I know I've gone a little over on time, but I'm going to wrap it up quick, and I look forward to your questions.